Stefanos's second lecture on the characteristic Lewis problem and general relativity.
Thank you, Yakov. So we spent 1 hour yesterday, the day before yesterday, introducing the characteristic in gluing problem in general, right? And we consider at the end the special case of the wave equation. So today I plan to finish the discussion for the wave equation. I'll try to give you as many details as possible, and I'll also give you a few applications. The applications will be mostly on the dynamics of black holes, and there will be emphasis on extreme black holes. Now, the reason I want to do this is because tomorrow will be fully nonlinear. Tomorrow we will start with geometry, uh, because the problem will be for the gluing problem of the Einstein equations, and this is purely geometrical problem. So we'll look a little bit more in detail at geometry. We will look at the results, we look at the proof, and we will look at applications. And as you will see, there are some interesting applications regarding extreme black holes, and more specifically, the third thermodynamical law. So everything I will say today will be linear, but our mind will, but as you will see tomorrow, everything will be generalized in the nonlinear case. All right, so let's start a little bit with a gentle reminder of what we discussed. We discussed a gluing problem where we have two regions satisfying some kind of equation, each of them. So you have a specific field satisfying an equation, and then you want to find a bigger region which has a field that satisfies an equation, and the restriction of that big field in each of these domains is retrieves the original ones in each of them. And we said you can try to glue space-times, or you can try to glue Riemannian slices of space-times. And in the first case, the law you need to satisfy the Einstein equations themselves. In the second case is the subset of the Einstein equations, which is known as the constraint equations, which are satisfied for the Riemannian metric and the second fundamental form on Riemannian slices of Lorentzian manifold satisfying the Einstein equations. And the simplest case, again, for such a problem would be to consider an equation that is as simple as possible, right? And anyway, so for the Riemannian slices, the most important result is this one. It's the result that basically initiated the field that says that any asymptotic flat solution can be glued in the asymptotic region, so far away from any kind of center, to a specific initial data set. All right, this is Riemannian. And then what we discussed is, okay, we want to, instead of trying to glue space-times or to glue in the space direction, we try to glue in the null direction. And in order to do that, we need to be a little bit familiar with null geometry. I will discuss this a little bit more tomorrow, but for now, I want to remind you that the interesting about the definition of null hypersurface is the one for which is normal vector is null. That normal vector, since null is also tangential, so it generates integral curves, which turn out to be null geodesics. And these are the null generators, and these are the white curves, for example, that you see here for each of these two surfaces. And two null hypersurfaces, the cross sections in this picture, for example, are spheres, okay? And given a sphere, as we discussed last time, there are precisely two null hypersurfaces that you can initiate starting from that sphere, the outgoing and then the incoming one. Now, something very, very important for what we will say today is that the geometry on S0 is purely Riemannian, okay? If you try to go along, if you look at the directions tangential to the null generators, then it's of course null. But every other transversal direction is orthogonal to the white one, and moreover is Riemannian. It's a space-like. So, given, for example, two such null hypersurfaces, or even one of them, and you were given a section to your null hypersurface, then you have an induced Riemannian metric on that sphere. what will be extremely important is that we will have the choice to also equip a given section of your null hypersurface, for example, only S0, with the unit round metric. Okay, we can consider coordinates theta, comma, phi. We can write the induced metric, the original one, in terms of these coordinates theta, comma, phi. But we can also consider the unit round metric on top of that. And then what we can do is that we can propagate that unit round metric along these null generators. So if I consider another section, to our null hypersurface, then you also have the unit round metric defined on it, on top of its induced Riemannian metric. Okay, so any section of our null hypersurfaces, will have two Riemannian metrics. The first one will be the induced one, and the second one will be the round metric, which is propagated along these null generators. Okay, you assume that the spherical coordinate system theta, comma, phi that you consider is it flows under this under the flow of the null vector field here. So if you have the theta, comma, phi coordinate system here and the theta, comma, phi coordinate system here, then you have two metrics which look identical, and these are the unit round metrics on each of them. So I spent already 3 minutes discussing this unit round metric on each section of your null hypersurface. But as you will see, this is the key, basically, if you want to derive the full theory of the gluing problem for the wave equation for a general null hypersurface in a general Lorentzian manner. Everything I said basically is for one null hypersurface, but as we said last time, you can basically introduce optical functions, which means two-parameter family of null hypersurfaces, two-parameter family of sections, which are intersections of your null hypersurfaces, and that will give you a double null foliation. This is, by the way, the theta, comma, phi coordinate system. Here I call it theta 1, theta 2. You see, you start with a coordinate system originally, and you propagate it along your yellow curve, which is just the null generator. So whatever value you have here for theta 1, theta 2, you also have it here, theta 1, theta 2. Of course, the optical, the null coordinates, the optical values change here. One of them does not change because you are on the one null hypersurface, but the other one changes because you change the incoming null surface as you go from here to here. And as we said, in this way, you can define a double null coordinate system, u, v, theta 1, theta 2. uv tells you basically on what section you are on, and theta 1, theta 2 tells you at what point of your section you're on. And with respect to that double null coordinate system, you can write your general Lorentzian metric like that. Yakov, by the way, told me that he uses a minus sign here. But anyway. This guy here is the induced metric on each of these sections. Okay, A and B are the angular components of your metric, and this slash means basically you take the section. Now, something very important. This is, as I just said, the induced metric on each of the sections. This guy is what I just talked about before, their unit round metric on each of your sections. And we have one more metric, which is basically the guy sitting between this guy and this guy. Okay, so this is the unique metric, which is conformal to the original one and has the property that its volume form is the same as the volume form of this one. Okay, this is the representative of the conformal class of G slash. This metric also plays a fundamental role in the theory, in the characteristic theory. And this guy here is what we call the conformal factor. Again, this is a metric conformal to the original one, so it doesn't have to be the unit round metric with respect to these coordinates, but it is conformal to the original one. But what you need to know, what you know about this is that This guy has exactly the same volume form as this one. And okay. And whatever is left, which is basically conformal factor, is what you have here in phi. Given this coordinate system, of course, we have the coordinate vector fields. Here they are. And we have an associated frame, as we said, that you can write the rest of your geometry. I want to remind you that chi is the second fundamental form, is the derivative of the induced metric as you go from one section to another one. As you go from here to here, how does the metric change? That's the second fundamental form for null hypersurfaces. That's measured by chi. And you also have another very important Christoffel symbol, which is this guy here, which is known as the torsion. Okay, and it's given by that. Okay. These are things we discussed last time, right? Given two pieces of null surfaces, you have like this is your first domain, this is your second domain. You have some equations satisfied here, you have some equations satisfied here, and you want somehow to connect them in a characteristic way, like that. That's basically the essence of the characteristic gluing problem. And we said that this can be super simplified by, instead of considering these two bits here to be your domains, you just consider data on the sections only, S1 and S2. You get rid of these full null hypersurfaces. And what you keep on S1 and S2 is not just the induced information, the induced metric, but also information like extrinsic to S1 and S2, okay, that have to do with these null hypersurfaces. So on each of these S1 and S2, you have data, and these data are related to your null hypersurfaces that you have here. At S1 and S2 only, not away from S1 and S2. And what you want is somehow to define a field on a null hypersurface starting from S1 and S2 and ending at S2. So S1 and S2 are sections of your null hypersurface. And you want your field that's defined here, satisfying equation. And when you restrict on S1 to retrieve the data on S1, and when you restrict it to S2, you to retrieve the data at S2. That's basically the gluing problem, okay? And that's the gluing problem for the wave equation, for the Einstein equations, for Maxwell equations. That's the gluing problem. I'll pass this because this is just the same thing as we said last time, just a 2D representation. Okay, now let's spend a few minutes to see how we can solve this problem for the wave equation. First of all, what is the main result? The main result is that we start with a general four-dimensional Lorentzian manifold. Okay, for the Lorentzian manifold, we don't assume any equations. No Einstein equations, no symmetries, no nothing. Just some regularity. We assume that we are given a null hypersurface, so we are not constructing geometry, right? This is a decoupled problem. We assume we know the metric and we construct these guys. We assume that we have a null hypersurface, that it's regular, free of focal points, free of singularities, everything is good. And we also assume that for this null hypersurface, we have a section, we have a family of sections, okay, foliating our null hypersurface. And we can assume that the first section is S1 and the last section is S2. Okay, and here we also have a family of them. Now, this is a picture only on the null hypersurface, but you know, to some order, you can generalize this construction. All right, and introduce a double null coordinate system. And given that double null coordinate system, you can write your metric like that. And the level sets of one of your optical functions will give you, you know, sections on your null hypersurface, and these sections are exactly the sections you assume you have on your given null hypersurface here. All right, so that's the geometric setting. Now, what can we assume on S1? On S1, we will assume that we know psi and the transversal derivative of psi. Okay, let me here. Spend 1 minute. So this is S1. This is S2. Here is our null hypersurface. On S1, we will assume that we know psi. And we will also assume we know the transversal derivative of psi on S1. Transversal derivative meaning this guy. So that's the sphere data for the wave equation in S1. Now, here, as you see, let's look a little bit at the regularity. The regularity here is only first order transversal to S1. I could also include not just the psi itself on S1, but all tangential directions. If you call this vector field T for tangential, then I could also put T to the K for all K. All right, these are our sphere data. All the tangential directions at this point and one transversal direction at this point. And exactly the same thing we can define on X2. Okay, all the tangential directions at S2 and one transversal direction at S2. So these things could be given, okay? You know all these functions. And what you're wondering is whether there exists a solution to the wave equation that admits these, these derivatives at these given two spheres. The spheres are connected by a null hypersurface. So in order to see whether such a solution exists, you just have basically to solve the wave equation along the null hypersurface. Let's contrast this with the Riemannian problem, right? The Riemannian problem for the Einstein equations is non-trivial, of course. But for the wave equation, it's fully trivial because if you assume you have a Riemannian hypersurface, and I don't know, you have a section here and another section here, you call this S1, and you have S2, and you define sphere data here and here. So you define some derivatives for the scalar field on S1, S2. Then let's say whatever you want, tangential derivatives here, and one transversal derivative here, tangential derivatives here, and one transversal derivative here. Then finding a solution to the wave equation that satisfies this data at these spheres is trivial, precisely because there is absolutely no constraint going from here to here, right? The initial data, the space-like initial data are freely chosen for the wave equation on a space-like hypersurface. So the space-like gluing problem, at least when you look at one transversal direction, one normal direction, is trivial. For the null hypersurface, it's highly non-trivial. Okay, and let's see why. The reason it's non-trivial is because there is an equation. There is an equation that relates your data here to your data here. This equation, in some cases, for some geometries, generates conservation laws. In other geometries, for other like kind of null hypersurfaces, does not generate conservation laws. That's the main thing about the gluing problem for the wave equation. And the main result says that you can find a solution to the wave equation with given data on S1 and with given data on S2, provided that S1 and S2 are separated by a null hypersurface. Provided on null hypersurface, there are no conservation laws. So the first theorem says that the only obstruction to constructing such a solution to the wave equation, where you know your data here and here, is conservation laws on this direction. No other obstruction, no monotonicity, no nothing. Okay, it's an exact conservation law. And as I just said, if you try to solve this problem, there is no equation relating your data here to your data here, so they are free. So there's the gluing problem is trivial. But when you go from data here to data here, there is an equation. So let's see this equation. And let's see when this equation admits conservation law and when it does not. And then at the end, we will also see applications of these conservation laws. Okay, that's the plan. So this is the wave equation, okay? Now I switch from the little psi to the big psi. Sorry about this. This is the big psi, but it's exactly the same as the small one. So we are solving this wave equation on an null hypersurface. And that's what we get. This is very familiar. So what is dv? Dv is simply this tangential vector field T. That T here is what I call dv. What is y? Y is this transversal guy. A specific, very, very specific y, of course. Okay, it's a null vector in the transversal direction. That is also normal, to your sections. Okay, so y is also normal here. And this guy here. So you see the wave equation, not as an equation for a rescale field, where the rescaling factor is given by the conformal factor phi that I explained earlier. The wave equation in terms of this guy is a derivative in u, so a tangential direction along your null hyper surface, and a transversal derivative along your null direction. All right, so it's a transversal tangential derivative of this rescaled version of your field. And this double derivative is equal to, again, the conformal factor times an operator that it is purely angular. All right? Yeah. So the simplest example of this equation would be in the Minkowski case, where you get something like that, du dv du of r psi is some like an elliptic, the spherical Laplacian. So this is the wave equation of Minkowski. This is a conformal factor. This is the one null derivative. This is the other null derivatives. And this is the elliptic operator. This is just the Laplacian, the round Laplacian on the round sphere. In the general case of any Norwegian manifold, this guy stays almost the same. The only thing that we generalize is this guy here, the radius, which is now is defined in terms of the conformal factor that I told you earlier. And this guy gets massively more involved, right? Not only you have the presence of your omega, but you also have these lower order terms multiplied by these factors here. The precise structure of these factors actually turns out to play a role, especially in the applications, because it's the precise constants here. Even instead of having 1/2, if you had 1 minus 1/2, that would make huge differences, whether in deciding whether you have a conservation law or not. So whether you have gluing or not. Anyway, this guy here is the question we're solving. And what do you see? You see that since this is the question C has to satisfy, if you integrate in V, again, V is a parameter along your null hypersurface, okay? So V is 1 here, V is 1 here, V is 2 here, V is 1.5 here, V is 2 here, okay? This is how V increases. And dV is again in this direction. All right, so you want to integrate along your null hypersurface. What will you get? You will get precisely this, okay? The integral of this derivative gives you this. And then you integrate this guy again along your null hypersurface. So this now is the main question. Why? Because as you see here on S1, we have psi, and we have a derivative of psi, and on S0, sorry, again, I go from little psi to big psi, and I go from S1 to S2 to S0 to S1. Sorry about this inconsistencies here in notation. So this is the original sphere. In any case, this is the final sphere. This is up to first order derivatives. This is up to first order derivatives. So these are specified. Okay, these are specified. So this left-hand side is a function that's given to us. And what we want is we want to find a psi for which, if you consider psi along each section, and then you consider this elliptic operator of psi along each section, you multiply it with the conformal factor, and you integrate it, then you get that. If you find such a psi, starting from here, going here, going here, going here, and that final thing is given, then you have found a psi that solves this equation, and moreover, at the boundary satisfies, at both boundary satisfies the prescribed data. So what is the first idea? The first idea is to replace this elliptic operator by a general function. Okay, so you want to find here a general function which has a property that after you multiply it with a conformal factor and you integrate, you get something that's completely given. And then once you have these functions, then you want to see whether on each of your sections of your null surface, this function is in fact of this form. So the gluing problem for the wave equation is two pieces. The first one is the transport piece, where you just have to find a function whose integral is given. And then it's the elliptic piece. That guy for which you just found, you want it also to solve an elliptic equation. All right? You want to solve this. So you want it to be in the image. That guy here has to be in the image of your elliptic operator. It has to be of this form. So let's continue a little bit just to see it. The technicalities are just basic functional analysis, but I want to show them to you. And that's why I said today we'll not talk about linear things. All right, let's assume for a second that we have these functions for which this is true. Okay, so dealing with somehow the transport part, the integral part, let's say we have already done it. The big question is, how do I know the function I put here that satisfies this question is actually of this form? Right? How do I know that there is a psi for which q psi is this f? Of course, in order for this to be true, you're going to have to be in the image of q, which means has to be in the orthogonal complement of the adjoint of q. Which means that precisely this f has to be orthogonal to everything in the kernel of the adjoint. And here comes the thing that I told you will be extremely important. The fact that on each of our sections, this is a relation, right, for each of the sections. On each of the sections here, 1, 2, 3, 4, 5, on each of these sections, we have to solve an elliptic equation. On each of these sections, we have the metric, we have the conformal representative of the metric, and we have the round unit metric. It's now the time to use that round unit metric. What is the property of the, how is the round unit metric and the original metric are related? They are related in terms of the volume form. We know that the volume form of the original metric is this conformal factor, and that's how you define basically the conformal factor, times the volume form of the unit metric. And why do I care about the volume form? Well, I care about the volume form because I have integrals, right? This relation here is an integral relation along over each section. So instead of looking at this equation, and that's basically the biggest part of this problem. And as you will see, that also plays a huge role when you try to solve the gluing problem for the Einstein equations. All right, having everywhere the unit round metric. Replace this guy here, the volume form of the unit round metric. When you do that, you will introduce two powers of the conformal factor. So you split them, you put one with f, and you put one with the kernel of the elliptic. Why do I group them like that? Well, I group them like that because if you remember, in the integral, I don't actually have just the elliptic operator itself. I have this guy. And I want this guy to be f, right? I want this guy to be f. So phi f is this guy. So I want, when I integrate this guy over v, to know what the value is. And moreover, when I integrate this guy against this rescale version of your kernel over the round sphere, over each section, I want it to be 0. So if you call this group guy here, if you call it capital F, this capital F, as I just said, has to satisfy an integral equation along the null generators and an equation, an orthogonal equation along each section. All right. These are the two conditions I just mentioned. This is to glue your data, and this is to basically solve the wave equation, which reduces to this elliptic equation somehow. All right, now let's start with this. If the kernel, if this guy, right, is in the kernel of the adjoint, if the kernel of the adjoint is inexistent, then we are done. Because if it's inexistent at a point, it will be inexistent in a neighborhood of the points of that point. Okay, it will be zero for all for a whole neighborhood. And in that whole neighborhood, we can do whatever we want. We can solve this equation always because you don't have to solve for anything. And once you are free to do whatever you want in a neighborhood, then you work in that neighborhood and you make sure that in that neighborhood your integral takes whatever value you want in time. Okay, that's a neighborhood in time. Once you are free in a neighborhood of time, you're done. All right, that's what we're saying here. So what did we just say? If there is one section where the kernel of the adjoint of this operator is trivial, then you can do gluing from S1 to S2, regardless where your section is between S1 and S2. Okay? As long as there is one section where the kernel of the adjoint is trivial, done. You have done gluing. Now, what if the kernel is non-trivial at all points? Well, again, as I said, some very basic properties from functional analysis. The first one is because we're talking about elliptic operators on compact manifolds. You know, the dimension of the kernel is always finite, and moreover, at certain intervals, it varies smoothly. So you have regions where you have some control over how this kernel varies. All right, so you focus on these intervals of sections. And here is now the main lemma that allows you to basically solve the gluing problem, even in the case where the kernel is non-trivial everywhere. Let's assume that V is basically, gives you the value of V gives you the section you are in. These guys here are the span the kernel, okay, at each section. And so we assume that this guy for every V is non-trivial. So what do you want? You want to find a function rho, given a function rho, you want to find a function f rho, whose integral in V is given, right? This is basically, again, to satisfy the boundary condition, so to glue your two data. And moreover, you want this guy to be orthogonal to your kernel. And to be a little bit more technically correct, not just the kernel, you want to be orthogonal to phi times the kernel and guess the unit metric, okay? But this is what you want. And the theorem says that given any function rho, so in other words, given any sphere data on the sphere 1 and the sphere 2, there is a function phi rho that satisfies both of them if and only if that guy here is in the orthogonal complement of the intersection of all the kernels over all sections. So, you see, this guy, the rho guy, the guy that's given to you, has to satisfy this property. If you have kernel here and you have kernel here, but those two kernels are very different, so their intersection is 0, then those two kernels are not an enemy. You can still do gluing. All right? The enemy is not the existence of a kernel at a point or at every point. The enemy to gluing is the existence of common kernel. Common kernel means that you have kernel in the intersection for all sections. And if that happens, if that guy exists, all right, then you can only glue your sphere data provided that the difference of your sphere data is orthogonal to that common kernel. That's what this lemma tells you. This is not it's an elementary lemma. but it's not extremely easy to solve, to prove. Anyway, the second observation is that if you have at every point that kernel, and those kernels have an intersection, if you have an intersection, well, here I say that you don't, but I mean, if you have an intersection, that's what I mean here, all right? Then the functions which are in the common kernel for all your sections, these functions generate a conservation law, right? If you multiply them against this transversal derivative of your scalar field, and you integrate over the sections with respect to the round metric, this integral will be conserved independent on V. And the conservation of this guy is an immediate application of these three things, basically. Okay, just immediate. Now, one very important important remark, this theta is in the common kernel. So it is basically a function of the sphere, and it's a function of the sphere that lives over all spheres. I mean, it's a function over each section, right? It's a function here, it's a function here, it's a function here, it's a function here, and over each section, it gives you the kernel. It gives you part of the kernel of your associated elliptic operator. And it's the same function. Okay, that's the important thing. It's the same function, all right? It's the same function for section 1, 1.1, 1.2, 1.3. It's the same function, which means what? Which means this guy is independent of V. This guy depends only on angular coordinates. It's one function that you see over the whole null hypersurface. Okay? This guy depends on V because this is geometry over the null hypersurface. This, of course, depends on V. This guy does not depend on V, and this guy does not depend on V. All right. So what did we say? We said gluing is possible only for those data at the initial and final sphere for which their difference is in this space. If the difference is not in this space, then gluing is not possible. And if the difference is in that space, then you can do gluing. And moreover, for any function, for any solution to the wave equation, by just studying the structure of the existence of this orthogonal space, which is non-trivial, you can conclude that for any solution to the wave equation, not just the one you constructed in the gluing problem, but for any solution to the wave equation, this integral is conserved. And having basically your rho being here is equivalent to saying that the sphere data you give me at sphere 1 and at sphere 2 have the same value of this expression. If you see these things for the first time, it might not be extremely easy, to fill all the gaps, but that's what happens. So let's summarize the result because we only have 15 minutes left, also for the applications that I want to describe. The result says that for any null hypersurface, the only conservation law you can find for all solutions to the wave equation is of this form. Okay? Why it's of this form? We proved that if you have kernel, then you have these conservation laws. How can you conclude that these are the only conservation laws, independent of any other aspect of the geometry? Well, precisely because if your sphere data at one sphere at S1 and S2 respect this conservation law, then you can do gluing, which means that if you had the third conservation law, then you wouldn't be able to do gluing, right? But precisely because you can do gluing as long as these conservation laws are respected, that means that these are the only conservation laws that you can define you can possibly have on your null surface. And these are the only obstructions to gluing. All right, so these are the only conservation laws you can define. These are the only obstructions to gluing. And the conservation laws exist if and only if this guy here, which is the kernel of the elliptic operator, it's the adjoint of the elliptic operator, has a kernel of this form, 1 over the conformal factor times a function that it is independent of the section. This L is the dv derivative. It tells you that this phi is the same function over all sections. So you have common kernel over all adjoint operators for all your sections. So this is a purely geometric criterion on the existence of conservation laws. And as we said, this is a classification of conservation laws, which characterize when you have solutions to the gluing problem. All right, everything that I told you assumes that you start with the sphere S1, you finish at the sphere S2, and you propagate from S1 to S2 using a family of sections, right? A family of spheres. And on each of these sections, I consider an elliptic operator, I take the adjoint, I look at the kernel, and I decide whether I have conservation law so I can do gluing or not. What if I can go from S1 to S2 by following a different family of sections, right? Instead of starting like that and moving like that, what if I start from S1, I finish at S2, but as I go away from S1, I move like that? Different. Then I will have different spheres. I will have different use metrics. I will have different elliptic operators. I will have different adjoints. Will these adjoints have common kernel? If they do, then I will have conservation laws that I have to respect. If they don't, then I can do gluing. But if I can do gluing, that contradicts the result that I couldn't do gluing by following another foliation. So here is this refoliation result. If you start with the blue foliation and then you consider a new red foliation, then there is a very remarkable point-wise relation of the adjoint operators, not of the original operators, not of these operators, not of these operators, but of the adjoint operators, okay? If you look at any intersection of the original sections and the new sections at any point, then point-wise, the adjoint operator is a multiple of the adjoint operator of the one section is a multiple of the adjoint operator over the other section of the new one. And moreover, if this is not true for all functions, but it's true for all functions when the elliptic operator here, this adjoint operator, acts on functions of this form. Remember, we're not looking at exactly the kernel, we're looking at a rescaled version of the kernel. Remember, that's the rescaling of the kernel. And why do I have this rescale factor? Well, because I had to move from the volume form of the original metric to the volume form of the round metric. So this thing has no weights absolutely. And I'm sorry about this. I have this laptop for 3 years and it's the first time it did this. Very sorry, very sorry. Okay. Can you hear me? Everything okay? Yes? Okay, thank you. All right. Sorry. Let's move a little bit quickly. All right. So what I was saying is that, yeah, we have this property. So that means that if you have a conservation law with respect to a given foliation that starts from S1 and ends at S2, let's say the blue foliation here, then that automatically forces a new conservation with respect to any foliation starting from S1 and ending to S2, any foliation. Because that common function fit is basically seen by the adjoints of the elliptic kernels for any foliation. Okay. And moreover, if this is the conserved charge with respect to the one foliation, and this is the conserved charge with respect to the second foliation, then their values are equal. You might wonder, what is this guy f? And this guy f is something very simple. Remember, we have to define the transversal derivative of every section. The transversal derivative is null. Remember, it's normal and null, but in the transversal direction. But if it's null, then you don't have a unique way. You don't have a way. You need to be very careful how you normalize it. Okay, you cannot take it to have norm one because it's null. So there is a special way to normalize it with respect to your foliation. Now, when you normalize your transversal vector with respect to your sections, then that normalization is a little bit different. And that introduces this factor f here. So this f has nothing to do with the original f that I told you before. It's just, it has nothing to do, with this f here. Okay, it's just a geometric f. In any case, you can, for example, even if you take f to be 1, you can still get different foliations, okay? So you see, if in the case where f is 1, you have precise agreement for the conserved charges. So the theorem tells you that given one foliation and a conservation law with respect to that foliation, then for any other foliation, you have a conservation law and the conserved charges agree. Okay, if you don't mind, I will go for 5 more minutes. And maybe I will try to steal a few minutes from tomorrow. Thank you, Jakob. All right, this is the first result that we like the most basic result one can find, that it's the wave equation on Minkowski. Now I already showed you what is the wave equation for Minkowski. This elliptic operator, the Q, the strange one, is just the Laplacian on the round sphere. The elliptic the adjoint is the Laplacian. So you have a kernel. What is the kernel? The constant functions. So this guy here is times 1. Okay, times 1. And this is the y vector field. And the integral of this y vector field, the transversal derivative basically over scale psi, is conserved. The phi is the r. And now, this is also something we talked about the first time, in the first lecture. This is the Newman-Penrose constant at infinity. And we said that at infinity, you have a vector, a derivative of the scale vector field, which you have to further scale so that it's conserved along null infinity. We discussed null infinity, we discussed sections of null infinity, we discussed traces of null infinity, radiation fields, we discussed the Newman-Penrose constants. Now, what I want to tell you is how is this related to the theory we discussed? This is the elliptic operator that's present for the wave in the wave equation. Right? Remember, these guys here are very specific into what they are. And where is the adjoint? I don't have anywhere the adjoint. Yeah, I don't have the adjoint anyway. You can just write down the adjoint of this guy. It's more or less it looks very similar with just some signs flip. All right. Now, if you consider this guy in the asymptotically flat region, and you rescaled psi, so instead of looking at psi, you look at r psi, because that's the thing that gets non-trivial. And you take the limits as you approach infinity, then it turns out, for example, that this expression here goes precisely to 0. And if it goes to 0, you end up with something that has kernel, the constant functions. If this guy did not go to 0, then you wouldn't have kernel. So that's why I told you before that the structure of these terms and even the coefficients is very, very important. And how these geometric terms decay as you go to infinity in an asymptotically flat spacetime. All right. So it turns out that this elliptic operator get reduced to the round metric, the round elliptic, the round Laplacian at infinity. And that's conservation law for the same reason that you have a conservation law here, right? You have a conservation law at infinity. It's just that this conservation law, in order to be non-trivial, so that's not 0 equal to 0 equal to 0, you have to rescale everything by something. Okay? So what I'm just saying that even if you rescale everything so that quantities that have to do with the scalar field are non-trivial, even in that rescaling, your geometry still disappears. Okay? This non-trivial part, even after multiplying by r, this decays even faster than the r that you need to put so that your scalar field is non-trivial. So your geometry will not be an obstacle in having kernel at infinity, so it will not be an obstacle in having the elliptic operator, having the conservation law. All right. And here is what I meant. And one more thing, let's consider the event horizon. Let's assume that the event horizon is scaling. So let's assume we have a stationary space-time. Then the elliptic operator simplifies into this guy here. This is the round, this is the Laplacian, this is the torsion term, this is, again, the divergence of the torsion, and this is the trace of the second fundamental form in the transversal direction. And this guy here is extremely important. This is what we call the surface gravity. The surface gravity. Now, for sub-extremal spacetimes, by definition, the surface gravity is positive. For extremal spacetimes, the surface gravity is 0. If the surface gravity is 0, then this term disappears. This guy can be grouped with this guy. So basically, you get a derivative, you get a derivative. That gives you, in the case where this term is not here, it gives you conservation law. Similarly to the way you get the conservation law in Minkowski. If this guy now is non-z, then this z for the term, actually you can prove that this operator here cannot have kernel. And inexistent kernel means no conservation laws, it means always gluing. So along the event horizon, for sub-extremal black holes, you can always do gluing. For extremal black holes, you can only do gluing if you respect the conservation law. But even more important than the gluing is the existence of a conservation law in the extremal case. So you will see nonlinear applications of this slide here tomorrow. This is the conservation law in the extremal case. Okay, we have the event horizon, we have the transversal vector field y, and you have that an expression of this transversal derivative integrated over any section you want is constant, independent of the section, for all solutions to the wave equation. This conserved quantity, we call it h, and it's for the horizon, and usually we call it also horizon hair, because it's an expression that will always stay 1. It's constant. If it starts with the value 1, it will always be 1. So that means that even if your scalar field disperses away from your event horizon, on the horizon there will be a quantity which does not disperse. And such quantities, we call them hair, and that's why we call it horizon hair. And this is the horizon hair in the extremal hair case. It's a little bit more complicated. It has both transversal derivatives, zeroth order terms, and tangential derivatives. And these conservation laws have been generalized not only for the wave equation, but for linearized gravity. All right. I was hoping that I needed at least 10 to 15 more minutes to finish the applications of conservation laws for the dynamics of spacetimes. But yeah, let's do this tomorrow. All right, that's all I want to say for today. Sorry about that.